We're in section 3-8. If I had a differential equation that said y prime is equal to a, then I'd say, well, y prime, that's a slope, and a is the slope of a line, and so I got a line, there's a line, and it's got a slope, and the slope is a. If I solve that differential equation, I get the equation for a line, ax plus b. Okay, b is something that would be an initial condition, and that initial condition would establish the line crossing some point, and I have an infinite number of those lines with the same slope, and I'd say, okay, that's fine. Until I find my initial condition, I really don't know which line I'm talking about. Alright, so if I take a differential equation that's y double prime plus lambda y is equal to 0, and I look at that differential equation, and I end up saying that at 0 I'm going to be 0, and y prime at 0 I'm going to be 0, then what is this equation of? Well, obviously it's an equation whose slope is 0 passing through 0. Okay, we're going to try this different. We're going to try this as y prime at 0 is 0, and y prime at pi is 0. So if we did that, we'd say, well, here's pi, and when I pass through 0, my slope is 0, and when I pass through pi, my slope is pi. Okay, so I look at that and I say, well, what kind of a curve might that be? And if it came this way like that, and it was at 0, and did something like that, and was at, I missed, and was at 0 there, that could be the answer to that differential equation. But it could have just as well been something that did this, and went up, and went down, and went up, and came back, and was there. Or something that did it 3 times, or 4 times, or 1,000 times. So I got multiple equations, multiple curves that it could be, knowing the 2 endpoints. Okay, so that's where we start, and that's what we're going to do. We're going to consider solving problems that look like that, not knowing what lambda is, only knowing what the endpoints of the function are. And these things are going to be repeating functions. Okay, that means they keep on going, so they're in forever and ever type thing. Okay, so we'll come back and look at problem number 2. And 3-8, problem number 2. If you need any more theory than that, then read the rest of the section. 3-8, number 2. The eigenvalues in problems 1 through 5 are all non-negative. First, determine whether lambda is 0 is an eigenvalue. Then find the positive eigenvalues and the associated eigenvectors. Okay. Any Germans out there? Who was eigen anyway? Okay, so we have y double prime plus lambda y is equal to 0. We have y prime at 0 is 0, and y prime at pi is 0 for our initial conditions. Okay, so first we'll consider if lambda is 0. That was good. That doesn't even look like a 0. If lambda is 0, what's going to happen? Well, I'm going to have y double prime is equal to 0. So what does the curve look like? Well, if I'm going to solve that differential equation, I'm going to get it, it's going to be in the form y is equal to ax plus b. And if I take the first derivative, I get a, and if I take the second derivative, I get 0. Isn't that lovely? Now, y prime at 0 has to be 0. So that implies that a has to be 0. Yeah, that implies a has to be 0. So, that being the case, y0 is going to be 0. Lambda 0, 0 by definition is going to be, is the eigenvalue and what's the associated function? Well, the associated function is going to be y at 0 of x is going to be 1. Because if I take the derivative of that, I get 0, which I'm supposed to have, because y prime at 0 has to be 0, so that would be okay. All right, so the second part, what we're going to do is we're going to be weird and say, okay, we're going to say let lambda is going to be equal to alpha squared, which is going to be greater than 0. Okay, so that's going to be the case. Now, if we didn't do that, we'd have to carry a square root of lambda through the whole problem. So what we're doing is we're saving a bunch of ink by saying lambda is equal to alpha squared. And some authors don't do that. This author does, which is perfectly okay. That being the case, we have y double prime is equal to, plus sign, plus alpha squared is equal to alpha 0 squared y is equal to 0. With that, we have a characteristic equation, r squared plus alpha squared is 0. That characteristic equation yields r's that are plus or minus alpha I. Okay, so that's pretty cool. That's pretty normal. That's nothing funny there. Therefore, we have to have a general solution I misspelled general. G-E-N-E-R-A-L. Solution. And that solution is going to be y of x is equal to a cosine alpha plus b sine alpha. Okay, so that's pretty cool. And y prime x is going to be minus a sine alpha plus b cosine alpha. Okay, so now I've got that. Applying initial conditions. Applying, I think there's a y in it, applying initial conditions. Alright, so if we do that, we have y prime at 0 equals 0, which implies what? Now, if y prime at 0 is 0, then b has to be 0. I don't have a choice. And y prime at pi is also 0. So if y prime at pi is 0, then that implies that alpha pi has to have, is an integral multiple of pi. Because in order for it to be 0 at pi, this has to be a pi. Sine of pi is 0. So alpha pi is an integral multiple of pi. So what does that mean? Well, so the eigenvalues are what? They are n squared. And the associated functions, what are the associated eigenfunctions? Are associated, and n is going to be 1, 2, 3, because they have to be intervals. And the associated eigenfunctions have to be y of n cosine n pi. And again, n is going to be 1, 2, 3. Those would be the associated eigenfunctions. And at that point, we were done with problem number 2. So next we're going to go to problem number 4. So as we just did in problem 2, we're going to do something different. We found that y sub 0 is 0 and lambda sub 0 x is 1. That's from problem 2. And lambda is going to equal alpha squared, which is the same. And we have a characteristic equation y of x is equal to pi cosine alpha x plus b sine alpha x. So that's what we have. And we have a new set of initial conditions for problem number 4, which is y prime initial conditions, y prime at minus pi and y prime at pi are our initial conditions. So y pi at minus pi is 0 and at plus pi is 0. Boom, boom. Okay, so that being the case, we're going to get two equations. We're going to look at y prime. And so y prime at x is minus a sine alpha x and b cosine alpha x. And we look at y prime at minus pi and y prime at plus pi. Okay, so we see that we have alpha a sine alpha x plus b cosine alpha x, and we have an alpha, and that's going to be 0. Now I got a minus pi sitting in there for the x, but I didn't put it in on purpose. Minus alpha sine alpha x plus b cosine alpha x is equal to 0. Now why don't I have a negative sign here? I'm going to put one in and then consider whether or not I need it later. But it looks like I probably do. Okay, so that's what I have. So So from those two equations, what do we know? Well, if I put in a minus pi, then this becomes positive, and that's why that's a positive. Right. So from those two equations, we know that from that we get that A sine alpha pi has to equal B cosine alpha pi, which has to be 0. Okay, so if A is equal to 0, then B can't be equal to 0, otherwise you have a trivial answer. No, yeah, and then B can't be 0. And this means that the cosine of alpha pi has to be 0, which means that alpha pi has to be an odd multiple. Alpha pi is an odd multiple of pi over 2. Because at pi over 2, if alpha is that, then the cosine of 90 is going to be whatever. Okay, so what we're going to do is say, well, we'll continue on. The other case, if A is not equal to 0, then B has to be 0. I don't have a choice. And then the sine of alpha pi has to be 0. So alpha pi must be an even multiple of pi over 2. So for the positive, therefore, the positive eigenvalues are n squared over 4. And with eigenvectors, with eigenfunctions, yn of x is equal to cosine n pi over 2, x over 2. Okay? If n is even, and y of nx is equal to sine n x over 2 if n is odd. Okay, and with that, we are done with section 8-3.